Good morning, children. Welcome to chemistry class. In the previous class, you have learned the wave nature of electromagnetic radiation or wave nature of light. Isaac Newton proposed light, a stream of particles known as corpuscles. You have learned in the previous class that this corpuscular theory or particulate theory explained the phenomena of light like reflection and refraction successfully, whereas the interference, diffraction, polarization, etc. could not be explained on the basis of corpuscular theory. So Huygens introduced the wave theory. The wave theory explained these properties, that is, these phenomena, that is, diffraction, interference, and polarization.
Interference of waves. The phenomena of the light which undergoes refraction and reflection can be explained by the two theories of light. They are the corpuscular and the wave theory of light. But some of the other phenomena, such as interference and diffraction, can only be explained by the wave theory of light. We know that two or more wave motions travel in space at the same time. Sometimes these two wave motions combine and some physical effects take place. Interference is one such physical effect. When two or more waves cross each other in the same medium, they both interfere and an accident takes place. This accident is known as the interference of waves. Interference is the combined effects of the disturbance caused by each individual wave at the same place at the same time. This effect can be understood from the principle of superposition of waves. Principle of superposition of waves. To understand this concept of the superposition, let's understand some of the examples. When we drop a pin in a tank, we see some circular waves. When another pin is dropped, we see some more waves. These waves travel in the same tank, and at one time or another, they superimpose on each other. The resultant wave would have an amplitude which is the sum of the displacement due to the individual waves. The principle of superposition of waves states that when two or more waves traveling through the same medium simultaneously, the resultant displacement at any point is the vector sum of the displacement due to the individual waves. In our case, the pin is dropped in a ripple tank with two pins. If y1 is the displacement caused at a point due to the first source, and y2 is the displacement caused by the second source, then the overall displacement r at the point of interference would be given by r equals y1 plus y2. When both sources have the same amplitude, then y1 and y2 would be equal to y. When y1 is due the crest or trough, and y2 is also due a crest or trough, the resultant would be the maximum. And when y1 is due to a crest and y2 is due to a trough, or vice versa, the displacement would be minimum. When maximum displacement takes place, it's called constructive superposition, and when minimum displacement takes place, it's called the destructive superposition. When superposition of waves occur, they can be destructive or constructive. This physical effort, observed as a result of the superposition of waves, is called interference. The physical effect of the superposition of waves from the source vibrating with the same frequency and amplitude is called the interference of waves. The physical effect is in the form of vibrations in the amplitude of the resultant wave in a given portion of the medium. Interference is a special case of superposition of waves, which originate from different sources but have the same amplitude and same frequency.
Diffraction of light waves through an aperture. Now let us learn how the light waves get diffracted at an aperture. According to definition, the bending of a wave or its deviation from the original direction of propagation when it meets a small obstacle is called diffraction. The wavelength of the light waves is 5000 angstrom, which is very less compared to the wavelength of the water waves and sound waves, which are about few centimeters to meters. As the wavelength of the visible light is small, comparing to the wavelength of the incident waves. Hence, for experimental observation, diffraction of light waves needs small-sized obstacles. As we learnt earlier, according to rectilinear propagation of light, when light falls on the opaque object, geometrical shadows of small opaque objects should be formed. But as the obstacles are small, the light wave bends along the corners of the obstacles and slightly spread into shadows, and thus they are not sharply defined. In the case of monochromatic light, when the light wave is incident on the small object like hair or a sharp edge object like blade, due to the geometrical shadows are formed with dark and bright fringes. Thus, diffraction is defined as the bending of light waves around an obstacle whose dimensions is comparable to the wavelength of the incident light, and hence its spreading into the geometrical shadow.
Okay, we discussed what is a wave and the characteristic properties of waves, the relation between the characteristic properties of waves in the previous class. You have also learned the different types of waves like the mechanical waves and electromagnetic waves. In the mechanical waves, again, the two types, the transverse waves and longitudinal waves. And you have also learned the electromagnetic radiations or electromagnetic waves. Electromagnetic waves are the waves which are associated with varying fields of electric and magnetic fields. And the electromagnetic waves of different frequencies which are arranged from higher wavelength to lower wavelength to higher wavelength is said to be electromagnetic spectrum. You have learned that in the electromagnetic spectrum, the visible region is a very small part, and the rest of the radiations are classified into cosmic waves, gamma rays, X-rays, ultraviolet rays, the visible region, and infrared rays, the microwaves and radio waves. You have learned all this. When we move from left to right in the electromagnetic spectrum, the wavelength of the wave, that is the lambda, gradually increases. And you have learned all this in the previous class. Now let us see the particulate nature of wave once again. Once the particulate nature of wave proposed by the Isaac Newton was discarded, as it could not explain the properties of light like diffraction, interference and polarization. Again, some of the phenomenon like black body radiation, the photoelectric effect, Compton effect, and the variation of heat capacity as a function of temperature, and the line spectrum of hydrogen atom could not be explained successfully on the basis of wave theory. Okay, again, in order to explain these experimental facts, again the corpuscular theory or particle nature of wave was again introduced by Max Planck. The corpuscular or particle nature of light or electromagnetic radiation is again introduced by Max Planck in order to explain the phenomenon like black body radiation and the photoelectric effect. Let us see what black body radiation is. You know that when a solid is heated, it emits radiations. A solid is heated, it emits radiations over a wide range of wavelength or over a wide range of frequencies. For example, if a rod of iron is heated, it starts emitting radiation as the temperature increases. For some time it doesn't glow. It doesn't mean that it is not emitting radiations. It is emitting the radiations in the infrared region. We can't see those infrared radiations. When the temperature reaches a certain value around 1000 degrees Celsius, it starts glowing with a dull red color. Iron starts glowing with a dull red color when the temperature reaches a certain value around 1000 degrees Celsius. If it is further heated, the brightness of the red color goes on increasing and the iron rod becomes bright red. On further heating, it changes to orange color. On further heating, it changes to yellow color. That means the light emitting from the hot iron rod changes from dull red to red color, bright red color, bright red to orange color to yellow color, and then it emits white light at a temperature around 1300 degrees Celsius, that is 1550 Kelvin. It emits white color radiation approximately. If it is further heated, it changes to blue color. As the color changes, the brightness of the light also increases. As the color changes, the brightness of the light also increases. You know that red color has higher wavelength and blue color has a lower wavelength. That is, as we move from higher wavelength to lower wavelength, the brightness of the light gradually increases. If this trend continues, the radiations emitted by the hot iron body should cross the violet color also, and it has to reach to the ultraviolet region. The brightness, if it were continue, the brightness goes on increasing. But the experimental facts are showing that the brightness is increased to certain value only. After that, the intensity or the brightness of the radiation decreases. This is the actual fact. And this fact could not be explained on the basis of wave theory. What is a black body? All the bodies emit radiations of certain frequencies only. They emit or absorb radiations of certain frequencies only. Black body is a body which emits almost all the radiations and absorbs all the radiations. That is, a black body is a perfect emitter and absorber of all the radiations. Whereas the other substances do not emit or absorb all the radiations, they emit or absorb only certain radiations. Okay. Which body is a black body? Sun is a black body. Black body doesn't mean that the body which is black in color. What is meant by black body? A body which emits or absorbs all the kinds of radiations, that is radiations of all the frequencies, is said to be the black body. It need not be black in color. Sun is a good emitter and absorber of all these radiations. We are getting the radiations on the lighting and other radiations on the earth from sun only. Sun emits ultraviolet radiation, emits infrared radiation, emits visible radiation, emits gamma rays, cosmic rays, radio waves, and so on. So sun is a good example of a perfect black body. A nearby black body can be approximated by taking the black colored substance like carbon black, or a hollow sphere which is coated inside with platinum black. Platinum black is a fine powder of platinum which is black in color. A hollow sphere which inside coated with the platinum black and has a hole at the surface can be considered as an approximate black body. If the radiation enters into that hollow sphere through the hole, the radiation enters, reflects several times inside the body and all the radiations will be absorbed. When the radiations are actually fallen on a body, some of the radiations are absorbed, some of the radiations are reflected, and some part of radiations are transmitted through the body. But a black body absorbs all the radiations which are fallen on it. The black body, a nearby perfect black body, is approximated by considering a hollow sphere inside coating with the platinum black and has a hole. A black body is a good absorber as well as emitter of all the radiations, just like sun. Okay? When the radiations emitted from the black body are observed, the radiations emitted from the black body are observed. Max Planck obtained a graph like this. Lambda is taken on the x-axis and intensity is taken on the intensity or energy of radiation is taken on the y-axis. As the lambda value decreases, the intensity of radiation increases, reaches a maximum value and then decreases. At a lower temperature, also this kind of graph is observed. At any temperature, suppose this is a T1 temperature and this is a T2 temperature, where T2 is greater than T1. At a temperature when the intensities of radiations emitting are observed, the lower wavelength radiations have higher intensities compared to higher wavelength radiations. Lower wavelength radiations have higher intensities compared to lower wavelength radiations. According to classical theory, that is wave theory of radiation, the energy or the intensity of light depends upon the amplitude of the wave only. The intensity depends upon the amplitude of the wave. As the substance moves from higher wavelength radiation to lower wavelength radiation, the amplitude gradually increases because of that this brightness should increase continuously. But the trend observed is the intensity increased to a certain value, higher value at a certain wavelength, and after that on further decreasing of wavelength, the intensity goes on decreasing. Actually, what expected is the intensity should go on increasing by taking this path. Here also, at this temperature also, the intensity should go on increasing by that path. But instead of moving in this path, the intensity of light is reaching a maximum value at any temperature and then decreasing. This is the experimental fact. This experimental fact could not be explained on the basis of wave theory. The reason is, on the basis of wave theory, the energy or the intensity of the wave is depending on the amplitude but not on the frequency. If wave theory is right, the intensity depends upon the energy or intensity depends upon the amplitude only but not on frequency. So, when it is heated, when it gains energy at the same temperature, its intensity should go on increasing but it should not have any change in the color. But What observed is the color of the radiation varying from higher wavelength radiation to lower wavelength radiation as heat is supplied. As more and more heat is supplied, it is changing from higher frequency, higher wavelength radiation to lower wavelength radiation. That is, color is being changed. That is just like the color changed from red color to blue color in the case of hot iron rod. So according to wave theory, the color of the iron rod should not be changed. But actual fact is the color of the iron rod is being changed. That means the intensity is not continuously increasing. Intensity increased to a certain frequency, certain wavelength, then decreased. This fact could not be explained by wave theory. Okay. Why the intensity is decreasing after reaching a certain wavelength could not be explained by wave theory. The fault is intrinsic, that is in the definition of energy or intensity of the radiation. According to wave theory, the energy or intensity of the radiation depends upon the amplitude but not on the frequency. That is the defect. Okay. In order to explain this, the particulate theory or wave theory was introduced by Max Planck. Another phenomenon which could not be explained by this wave theory of radiation is photoelectric effect. Photoelectric effect is the phenomenon in which when light of suitable frequency is fallen on a clear surface of metal, the metal emits electrons. These electrons are said to be the photoelectrons, and this phenomenon is known as photoelectric effect. Suppose there is a clean surface on which light is fallen. A light of suitable frequencies or suitable energy is fallen on the surface. It emits electrons. Electrons are emitted from the surface of the metal. This phenomenon is called photoelectric effect. Okay. The electrons are present in the atoms present on the surface of metal. Those electrons are knocked out by the consumption of energy associated with the light fallen on the surface of the metal. If light possesses the wave nature, that is, if energy is continuous, the wave nature of radiation considered the continuous emission of energy. That is, if energy, radiant energy is continuous, that is, the radiation possesses only wave nature, the energy can be accumulated. All the radiations, that is the radiations of all the frequencies should emit photoelectrons from the surface of a metal. But experimentally it was found that only certain radiations whose energy is more than a critical value only are able to emit the photoelectrons. If radiation is or the energy is continuous, if the energy is continuous, energy can be accumulated and the radiations of any frequency or any color should emit the photoelectrons. For example, if this is cesium metal, the red color radiation also can emit the photoelectrons from cesium metal. The yellow color radiations also can emit the photoelectrons from cesium metal, and the blue color radiations also can emit the photoelectrons from cesium. For cesium, either red color or yellow color or blue color in the visible region can emit the photoelectrons. Whereas if we take potassium, the red color radiation cannot emit the photoelectrons from potassium, but yellow color radiation and blue color radiation can emit the photoelectrons from potassium. The red colored radiation has a frequency 4.3 to 4.6 into 10 to the power of 14 hertz per second. That is the frequency of red color. This red colored light can emit the photoelectrons, can produce the photoelectrons when it is fallen on cesium. But red colored radiation cannot emit the photoelectrons from potassium. Whereas the yellow color radiation has the frequencies from 5.1 to 5.2 into 10 to the power of 14 hertz per second. From this it is understood that yellow colored radiation has more energy. As we move from red to yellow, the energy, red to blue, the energy gradually increases. That is, as the frequency increases, the strength, the energy associated with that wave also increases. But according to wave theory, energy is not depending on frequency, it depends only on intensity. If a radiation of a red color or any other radiation which is less than the specific frequency is fallen on the substance, no matter how long the radiation is fallen on it, no electrons are emitted from the surface. So in order to emit the electrons from the surface, the radiation fallen on the surface should possess a minimum amount of frequency, minimum value of frequency. That frequency is called the threshold frequency or the critical frequency, which is known as, which is represented by nu zero. Threshold frequency is represented by nu zero. The threshold frequencies depend on the nature of the metal. Different metals have different values of threshold frequencies. For example, for lithium, the threshold frequency is 2.42 electron volts for lithium. For sodium, 2.30 electron volts. For potassium, 2.25 electron volts. For magnesium, 3.70 electron volts. For copper, 4.80 electron volts. For silver, 4.30 electron volts. For cesium, the threshold frequency is still less than 2.25, will be approximately 2 electron volts. Approximately 2 electron volts. That is, less amount of energy is required to eject the photoelectrons from cesium when compared to the other metals, the potassium, sodium, lithium, magnesium, silver and copper. So because of this, no matter how long the radiation is fallen on the surface, the energy is not enough to eject the photoelectrons from potassium if red colored radiation is used. On the other hand, yellow colored radiation or blue colored radiation are enough to eject the photoelectrons even from potassium. So frequencies of or radiations of higher frequencies having a frequency more than a certain value, that is the critical value known as the threshold frequency, are able to release the photoelectrons. But not all the radiations. But according to wave theory, the energy can be accumulated just like water can be accumulated in a bowl. Just like water can be accumulated in a tank, energy can be accumulated according to wave theory. As the energy is directly proportional to the amplitude. Energy is directly proportional to the amplitude of the wave. That is, energy is proportional to intensity of the radiation. Intensity of the radiation can be increased by the accumulation, so the energy should be accumulated, but it is not being happened. Energy is not being accumulated. If energy accumulates, the red colored radiation also can eject the photoelectrons from potassium. But the red colored radiation is not able to eject the photoelectrons from potassium. This phenomenon, that is photoelectric effect, could not be explained on the basis of wave theory. So in order to explain all these, Max Planck in the year 1901 proposed his theory known as quantum theory. Max Planck's quantum theory. According to Max Planck, the radiant energy is not continuous. A radiant energy is not continuous. That is, energy emitted or absorbed by the bodies in a discrete in the form of discrete frequencies, not continuously. Okay, a radiant energy is not continuous. Energy is emitted. Or absorbed. In the form of small packets. Energy is emitted or absorbed in the form of small packets known as quanta. A definition of quanta. Energy is absorbed in the form of or emitted in the form of small packets known as quanta. Each quantum is associated with some energy. Each quantum is associated with some energy. The energy of quantum is equal to or is proportional to nu, that is frequency. The energy of quantum is proportional to nu, that is frequency. is proportional to nu, or is equal to some constant h into nu. Okay? Where h is called the Planck's constant. Its value is, he calculated its value is 6.625 into 10 to the power of minus 34 joule second, or 6.625 into 10 to the power of minus 27 erg second. 6.625 into 10 to the power of minus 24 joule second, or 6.625 into 10 to the power of minus 27 erg second. Next one is the total energy of radiation. The total energy of radiation depends on intensity. The total energy of radiation depends on intensity. As the intensity increases, number of quanta released will increase. If total energy E total is equal to N into H nu, where N is a number which represents the number of quanta emitted, the number of packets of energy emitted. If the intensity is more and more number of quanta are emitted, but the frequency will not be changed. The frequency will not be changed. Only number of particles will be increased. Number of energy particles or radiation particles increased. Okay? So these are the postulates of Max Planck's quantum theory. Max Planck suggested that radiant energy is not continuous, it is quantized. Quantized means it takes only discrete values. Energies of discrete values are only emitted, not all the radiations. Energy is not emitting continuously. Only it is emitted in the form of small packets, that is one after the other. Energy is emitted in the form of small packets, one after the other. If the intensity of radiation is more number of quanta are emitted. So total energy will be more. The energy associated with each quanta depends upon frequency only, but not on the intensity of the radiation. Energy doesn't depend upon the intensity of the radiation, but on the frequency. But according to wave theory, energy associated with the radiation depends upon intensity. But according to Max Planck quantum theory, radiant energy depends on both frequency and intensity. Radiant energy depends on both frequency and intensity, not only the intensity but also the frequency. The energy of each packet depends upon frequency. If the number of packets are more, the total amount of energy released will be more, that is, the intensity of the radiation will be more. What is meant by quantization? Quantization means taking definite values. If you are traveling in a taxi, you will find 2 meters in the taxi. One is speedometer, and the other is fare meter. Speedometer and fare meter. If the accelerator is pushed, the speedometer shows all the values from 0 to the highest value. When the vehicle starts, suppose this is the rider moves on this. This is the scale. Suppose this is 0 on the speedometer. This is 180 kilometers per hour. When the accelerator is pushed, it slowly moves and shows all the values. It shows all the values. This kind of moving through all the values is said to be the continuous variation. It's said to be the continuous variation. On the other hand, you will find a fare meter also. Fare meter. This shows kilometers and fare. Kilometers and fare. If the taxi is started, it is set to a minimum value, that is the minimum value of distance, that is 2 kilometers. For 2 kilometers, suppose the fare is 20 rupees. For 2 kilometers, this fare is 20 rupees. Till the taxi travels 2 kilometers, the meter, the speedometer, the fare meter shows 20 rupees only. Speedometer shows 20 rupees only. When 20 meters line is crossed, 20 meters are crossed, then this shows 3 kilometers, and the fare will show, fare meter shows 30 rupees. In between 20 and 30 there are so many values, all those values are discarded. It jumps from 20 to 30 in the fare and jumps from 2 kilometers to 3 kilometers in the kilometers value. Here the readings are changing, readings are taking only discrete values 2, 3, 4, 5 and so on. Here the fare is taking the values 20, 30, 40, 50 and so on only, but not taking all the values in between 20 and 30. But it is not the case with speedometer. Speedometer, a rider shows all the values from minimum value to maximum value. That is, the readings given by the speedometer are continuous, whereas the readings given by the fare meter are discontinuous. It is limited to discrete values only. This kind of taking discrete values is said to be the quantization. In a kirana shop, if there is an electronic weighing machine, you can get 1 kilogram of sugar, 1.1 kilogram of sugar, 1.1 kilogram of sugar, 1.2 kilograms of sugar, 1.3 kilograms of sugar, 1.3 kilograms of sugar and so on. But in a supermarket, you will get half kilogram of sugar, 1 kilogram of sugar and 2 kilograms of sugar only. 2000 grams of sugar only. 500 grams, 1000 grams and 2000 grams only. That means the selling of sugar in the supermarket is taking only discrete values, that is a discontinuous manner, whereas in a kirana shop you can get any amount of sugar, and according to this sugar you will get the you need to pay the money. If 1.1 kilograms of sugar taken, you have to pay for 1.1 kilograms. 1.2 kilograms of sugar is taken, you can pay for 1.2 kilograms. But it is not the case with the supermarket, in which the packets are made ready. 500 grams packets, that is half kilo packets, 1 kilo packets and 2 kilo packets are available. You can take either 500 grams or 1000 grams. You cannot take the sugar in between 500 and 1000 grams in a kirana shop, in a supermarket. That means the values are quantized in the supermarket, whereas the values are continuous in the kirana shop. In the same manner, radiant energy is quantized. That means the hot bodies emit radiations of certain frequencies only, that too they emit the radiations in the form of packets but not continuously. These are the suppositions of Max Planck's quantum theory. By using this quantum theory, Max Planck successfully explained the black body radiation. Let us go to the black body radiation once again with respect to the Planck's quantum theory. Lambda is taken on the x-axis and intensity is taken on the y-axis. Intensity is taken on the y-axis. According to Max Planck, when a body is heated, the particles are set into vibration. The particles are set into vibration when the body is heated. If more and more amount of heat is supplied to the body, the amplitudes of the vibration increase, and at the same time, not only the amplitudes, and at the same time, the frequencies also increase. the frequencies of the radiations also increase. As the frequencies increase, the color changes from red to blue in the visible region. But according to the wave theory, as the energy depends on amplitude only but not on the frequency, the radiations of the same color with higher and higher intensities are to be emitted. But according to Max Planck's quantum theory, as the body is heated, it gains energy, and not only the intensities but also the frequencies increase. That is, the radiations emitted move from higher wavelengths to lower wavelengths. Because of that, the color of the radiation changes from red to blue gradually. So in this way, the variation of color from red to blue is successfully explained on the basis of the quantum theory. On which postulate the energy associated with the radiation depends on frequency, but not only on the intensity of the wave or amplitude of the wave. So in this way, this property is successfully explained. The photoelectric effect also explained successfully by Einstein. Photoelectric effect is successfully explained by Einstein based on quantization of energy. When a radiation of certain frequency is fallen on a clean metallic surface, it ejects the electrons. The emission of electrons is said to be the photoelectricity, and the emitted electrons are said to be the photoelectrons. We discussed that red colored light can emit the photoelectrons from cesium, but it is not able to emit the photoelectrons from potassium. Whereas the blue colored light is able to emit the photoelectrons both from cesium and potassium. The reason is, when the light is fallen on the surface of the body, the entire energy associated with the packet of energy, that is quantum, the total energy associated with the quantum is supplied to the energy electron, is supplied to the electron on the surface of the metal. That is, the electron at the surface of the metal gains the entire energy of the packet of energy. In the case of light, this packet of energy is called photon. Einstein named this packet of energy, that is quantum, as photon for light, that is visible light. For visible light, the quantum is named by photon. If a photon of enough frequency is fallen on the substance, the energy associated with the photon is taken by the electron. As a result, its kinetic energy increases. The energy of the electron increases. If energy of electron increases, it overcomes the force of attraction from the nucleus. That means some part of this energy associated with the photon works against the binding energy. Binding energy is the amount of energy which is responsible for binding the electron in the metal. That is nothing but the attraction between the nucleus and the electron. That energy is to be overcome. Some of the energy gained by this electron is used to overcome, that is used to do some work against the binding energy, and the rest of the energy is converted into kinetic energy of the electron. That is, energy of ejected electron, energy of photon is equal to energy required to overcome the binding energy, that is E0 plus kinetic energy. The total energy of the photon is gained by the electron, some is utilized to do the work, that is E0, and the rest of the energy is converted into photoelectron. This E0 is also known as work function. E0 is also known as work function. If the energy associated with this photon is that is h nu, where nu is the frequency of the radiation fallen on the substance, and nu 0 is the threshold frequency, that is the minimum frequency of radiation required to eject the photoelectron, nu 0. The total energy required for the turn is h nu 0. That means W is equal to h nu 0 and K is equal to half mv square. So h nu is equal to h nu 0 plus half mv square. So if the energy, if the frequency of radiation fallen on the surface is not more than this nu 0, it will not eject the photoelectrons. If radiation nu is exactly equal to nu 0, if nu is exactly equal to nu 0, then kinetic energy of the electron is equal to 0. Electron is just knocked out, but it doesn't possess any kinetic energy. In this way, from the particulate nature of radiation suggested by Max Planck, Einstein successfully explained the photoelectric effect. Okay. Suppose in the photoelectric effect, suppose the electron emitted possesses some kinetic energy. In order to stop that electron, we need to apply some potential. Electron volts applied to stop the potential. That means in order to stop the potential, the kinetic energy should be made equal to 0. That is, velocity of electron should be made equal to 0. For that purpose, the energy applied against to the ejected photoelectron should be equal to kinetic energy, that is equal to half mv square. This energy required to stop the photoelectron, that is to make its velocity 0, is said to be the stopping potential. Stopping potential. The stopping potential of photoelectron is equal to half mv square. Okay. So some of the phenomenon of light like interference, diffraction and polarization are explained only from wave theory, and some of the phenomenon or facts like photoelectric effect and black body radiation can be explained only by the particulate theory, that is the particle nature of light. So from this we can conclude that light possesses both particle nature as well as the wave nature. Radiations are emitted in the form of particles, but propagate in the form of waves. So we can conclude that the radiations emitted in the form of particles but propagate from one place to the other place in the form of waves. So in this way, radiations possess both particulate nature as well as the wave nature. So let us continue the other topic, that is atomic spectrum, in the next class.